What if I told you that when you create a file in Linux system, so you use commands like vim or nano or touch to create a new file, like I created that marek1.txt file in home marek, which is my home directory, that marek1.txt is not my file. And from the Linux system perspective, the location of that file is not even in home marek directory. When you create a new file, your computer will save this file physically on the disk, and then it will create something called a regular file inode. And that regular file inode will store all information about my file, like when the file was created, what is the current size of this file, and where exactly this file is on the disk. So you might ask, what is that marek1.txt then? What it is for? Well, that is completely different entry in something called a directory inode. And the directory inode will store information about current files and folders that can reside inside that directory, and it will also store their corresponding regular file inode identifier. And you can create multiple entries in different directory inodes that will point to exactly the same file, and those entries are called hardlinks. And I know, at this stage it might be very confusing, but we will have a look at each of those components now in more detail, and we will see exactly what it is about. And by the way, maybe you heard the saying that in Linux everything is a file. And that's true. And what it really means, that what we are talking about today is really a foundation of Linux operating system. That's why it's so important to understand what really is going on under the hood when you read or modify or remove your file. So let's get started. It all starts with some storage. We either have a hard drive or USB drive or other media that is capable to store the data. And that storage, maybe it's SSD drive, will either have already created something called partition and file system, or maybe it's completely blank and we will have to create a new partition and a file system for it. What I want to focus on is the file system though. When a file system is being created, like Linux ext2 or ext4 for example, within that file system there is a block of data that is reserved for something called inode table. When you create a file system, this inode table is automatically created, and we can use command like df-i to see the maximum number of inodes that can exist in that table. We will see separate information for each partition, because each partition will have separate file system, and each file system has its own inode table. We can see here how large is the table, what is the total amount of inodes that can exist in that table, and then we can also see how many of those inodes or inode IDs we already have used, and how many of those entries we have left. You will also see the size of the inode table for each different partition. You will also see that the size of the inode table is different for every single partition. That's because it will depend on the file system used, the partition size, and some other things. That's why you eventually will end up with different size of inode table for every single partition. So now we know that we have some inode table and some inodes inside it. But what are those inodes for? How useful they are for us? Let's start maybe with that thing called regular file inode first. I already created a file called marek1.txt in my home directory, which is /home/marek. So I will make sure I'm inside of my home directory. Okay, so I'm inside it, and you might already know a command ls-l. When we run that command, we usually check the permissions for that file or size of that file. In this case it's an empty file, but we usually omit that number which is in second column. And the most common number you will see here is anything between 1 and 3. It can be more, but it won't be less than 1. And this number is pretty important. It will tell us how many hardlinks point to the same inode ID. For my newly created file, marek1.txt, I can see only one such hardlink. And I can see its size is 0, that's because I just touched it, I didn't write anything to it. But now we can run a command like stat marek1.txt, which will show us some inode metadata information regarding my file. And I can see the inode type, which is regular file, regular empty file, it even says exactly. I can also see current number of hardlinks. It just says links, and it says 1. And it's the same number as we saw in previous command output. That is because there is currently only one directory inode entry that points to this inode ID. Inode ID is here, 262.438. That's our inode identifier for file marek1.txt. Or not for file, but for that entry in directory inode, okay? This file information really comes from directory inode because regular file inode has no idea what is the name of the file. This inode ID will only know that there is currently one hard link pointing to it, but it doesn't care really what the name in the directory inode actually is. The only information the regular file inode stores is that digit, and it's currently 1. It knows it has one hard link pointing to inode ID 262.438. I can see here also birth, which means when the file was first created. I can also see when inode information was last changed, and when the data in the file itself was last modified. Regular file inode will also have something called data block pointers. And they are pointers to exact location of my file on the disk, like where physically my file is written on the SSD itself, which data blocks are taken by this file. And the inode might have many of those pointers because your file is usually saved in multiple data blocks, so inode will keep track of all of those data blocks on physical disk that the file will occupy. I can also see here when the file was last accessed, what are its permissions, and the most important, the inode identifier. There is another command, it's ls-li. This command will give me a simplified view, which will also include the inode identifier for my file, or its entry in directory inode. This command simply combines information from directory inode and from regular file inode. But what that all means to us? Why is it important at all? Let's see what really happens when you create a new file. So I created that file called marek1.txt. Our system will create a new inode identifier for that file. We can see it created inode 262.438 for what I called marek1.txt. And now this inode ID will keep track of this newly created file. It will know where to physically find this file on the hard drive. It will track its current size, because size is something that can change in time. It will also track the file permissions, etc. And that inode ID is enough for our operating system to work with this file. So what is that entry in directory inode for then? That marek1.txt. And I like thinking of this entry in directory inode as if it was a DNS entry. So if you type in your browser youtube.com or google.com, your operating system looks at that, or browser, let's say, looks at that and says, what the heck is that? And your browser will forward that query to that name, google.com or youtube.com, will forward it to DNS server saying, hey, Marek is typing some crap like google.com, what does he mean? And DNS responds, yeah, ignore him. What he really means is the IP address of 146.1 blah blah blah, whatever IP address of that server is, of google.com or youtube.com. And we have exactly the same situation here. Our system, or Linux kernel to be precise, uses inode ID to locate, write and modify that file. The other entry, that marek1.txt, is created for us, so we, as human beings, can work with the file using its name rather than inode ID, because it's so much easier for me to remember marek1.txt than ID of the inode that was created for the file, for the physical file on the disk, I mean. So when I type /home/marek/marek1.txt, my system will translate that human readable format to a series of inode IDs, which we will see shortly, which is something that system can simply work with. And notice that they are two completely separate identifiers. The only thing that a regular file node ID will be aware of, and it will be tracking, is the number of current hard links. So when you create a new file, like I created my file marek1.txt, the inode itself will make a note that I created first valid entry in directory inode, that then points to this regular file inode. But regular file inode will only reference current number of active hard links that exist in the directory inode. The regular file inode itself couldn't care less what is the name of my file. this information is completely irrelevant for the regular file inode, so it doesn't even bother to save this portion of information. For regular file inode, it's only important if there are some external links in directory inodes that point to this regular file inode. And what I can do, I can create different names now in different folders that will point to the same regular file inode ID. And because I will point them to exactly the same inode, all of them will be able to read and write to exactly the same physical file on the disk. Let's do it now. Maybe first I will change the content of the marek1.txt file to clearly show that we are reading the same file. Let's do vim marek1.txt, and I will put something like, doesn't really matter what, wq. So now, if I run cat marek1.txt, I can see this is the output, or this is the content of my file. Maybe let's clear that. So let's now create another pointer in the directory inode that will point to the same regular file inode. And to do that, we use command ln, And then I put the name of my existing file, which is marek1.txt, and the name of the new file. And the new file doesn't have to exist. The new file name, I should say, the new file name will be automatically created for us. And I will call it, maybe, I don't know, marek77.jpg. And I know JPEG extension makes no sense here, but both me and Linux do not care about file name extensions. I just want to make it completely different, the name. I just press enter, and if I run lsl now, I now created a new entry. It's in the same directory inode though, because we are still in home marek directory. But I created a new entry that points to exactly the same inode ID. I can already see something changed. The number of hard links changed for both files to 2. So we've got one physical file on the disk, we've got one regular file inode for that file on the disk, but we've got two external pointers, because we've got marek1.txt and marek777.jpg, they both point to the same regular file inode now. So if I run cat marek777 now, .jpg, I can see the content of the same physical file on the disk. Also note that the new file name does not have to be created in the same folder. You can create it anywhere you want. Let's create another pointer, that hard link, to the same inode ID. So I can use the ln command again, and now it doesn't really matter if I use marek1 or marek777, because that part isn't really what will be used anyways. We only want to grab the corresponding inode ID for that file name, and that will be used instead. So let's say maybe marek777. As my existing file, and the new file, I want to put it in temp folder. So it's /tmp / whatever, maybe marek5.txt. I just press enter. If I run lsl now, I can see now we have 3 hard links already, but the file is not in this directory, it's in temp directory now. So if I cd temp and run lsl here, okay, this is some pre-existing crap, that it's not mine, but we can see marek5.txt file here. If I run stat on that marek5.txt file, let's run the stat for the previous two as well. I should have used space, but you can clearly see we've got 3 links, 3 hard links, pointing to exactly the same inode identifier. And I believe the inode ID has changed since then, but that sometimes happens. I don't want to dwell too much, but what's important is currently we've got 3 files, marek5, marek1 and marek777, which are even in different folders, that point to exactly the same regular file inode ID, 262.441. What I mean, well, the inode ID changed because we can see now we've got a regular file, not a regular empty file. This is different type of inode. It's very similar, but it's slightly different. That's why we ended up with new inode ID. But the physical file on the drive is still the same. And note that these are not copies of my file. These are only pointers to exactly the same file. When you copy the file, it will take twice as much disk space, and then the new inode will be created for that newly created file. Here, we are not talking about the copying process. What we have here is a single file on a hard disk, but it will have 3 different references or pointers in our file system. We have 3 entries in 2 different directory inodes. Okay, so now let's talk about removing the file. Or if we want to be precise, we should call it unlinking the file. When you create new entry in directory inode, it's called linking, because you link a file name in directory to regular file inode. And now we will start unlinking the directory inodes from the regular file inodes. Let's maybe clear that first. Let's go back to my home directory. And now let's remove those entries. Now the question, have I removed the physical file on the disk? Well, no, I haven't, because we still have one hardlink entry in the temp folder. If we go back to the TMP folder and we run lsl here, we see that marek5txt file here, file name, and we can see number of hardlinks dropped to 1, because this is the last existing hardlink that points to regular file inode. And if I run cat marek5txt, we can see the information is still available for me in that file. But the question now is that, if I run remove marek5txt, have I removed the file now? The answer is, unfortunately, we don't know. When we remove the last hardlink, what happens first is that regular file inode will decrease the number of current hardlinks to 0. But that is the first condition for the file and the inode itself to be removed. But it's not the only condition. If there is another process currently reading, writing or modifying my file, this file and this inode will keep existing. The processes that are currently running on that Linux system do not care about the fact that some directory inode entry was removed, because that name of the file was never used by them. The processes were only interested in corresponding regular file inode ID. So like with DNS and that IP address in previous example, what your browser really does, it goes to IP address, not to name google.com or youtube.com. And here, the running process also will not use the name, it will only use the regular file inode identifier, not the name used in file system structure. And that inode ID still exists. And even though the current number of hardlinks pointing to this inode ID equals 0, it might not be removed immediately. What this only means that we, as users, we can't point new processes or programs to that inode using file name, because we don't have any file names for that inode ID anymore. But existing processes that are working with this file will continue to do so, because if regular inode ID still exists, that's all they care about. And this sometimes might lead to unexpected scenarios, where, for example, you can see you start running out of disk space. So you jump in and you decided that you will remove some large files. And you run maybe, I don't know, remove marek5.txt as we did for the last file. And then you check the available disk space after running that command, and you can see that nothing has changed. Or even worse, you keep getting less and less space available on the disk. That's because maybe something is still writing new stuff to that file that you thought you removed. If you know which process it is that is writing to that file, referenced by inode ID, you can try to kill that process, and only then the file will be removed. When we have no other processes writing to the file, then those data blocks will be marked as ready to be written to, and the regular file inode will also be emptied, and it will become ready to be reused for some new files when needed. So that's something important to bear in mind. So just to summarize, regular file inodes will store all the metadata about your file except of the file name and the file content itself, because file name is kept in directory inode and content is kept separately on the disk. Let me now quickly mention something else. If there is that thing called hardlink, does it mean we also have softlinks? And the fact is, yes, indeed, we have softlinks, and the only difference between hardlink and softlink is that softlink points to the file name already existing in directory inode ID. And the command to create a softlink is nearly exactly the same. Let me show you. Let's go back to my home directory. You can see there are no files. Let me clear that. I will touch file, maybe mark1 again, And I previously used that command. ln, the existing file, and the new file. That created a hard link. So to create a soft link, I just add -s here after ln command. Let's press enter. If I run lsl now, you will see a little L in first column, and you will also clearly see what that soft link is linked to. So that new file, marek777, links to the file name, not the inode ID. So if I remove marek1.txt now, as you can see, we are left with a soft link, but it's already, we can see something is wrong with it. It's red, because we lost the information it needs. This soft link is now useless. You can see no such file or directory. We can run stat on it, and you can see symbolic links will have their own inode identifiers. This is inode identifier specifically for symbolic link. But let me remove it now, because, as I said, it's pointless to keep it if we remove the original file name. And as you can imagine, creating a soft link does not increase number of hard links in regular file inode, because soft link does not point to inode, only hard link does. Let's now talk about those directory inodes a bit, because we saw them, but we didn't really talk about them. We could see that I have some pointers called hardlinks that we can create in directory inode. But what is the directory exactly? Those directories that either we or a system creates for us, that entire directory tree that starts with the root folder, this is all built based on directory inodes. Directory inode will keep a bit different information than a regular file inode does. And we can check what is the inode ID for each directory. And for that we run exactly the same command as before. Let me clear maybe again. I am in home Marek, in my home directory. So now I can simply run stat /home/Marek. You can see yet another type of inode. This is directory inode. And these type of inodes are used by our file system to build that tree-like file system that we as users can then use to read and create and write to new files and folders. But first thing, you might be curious why there are already two hard links included in this inode information. Look at that. Links 2. What are they? This is empty directory, isn't it? There are no files, so what are they, those links? If you run lsla command, you will start seeing hidden information. And you will see that even empty directory, even if I didn't have those files, bash and profile, etc., even if it was completely empty directory, you would still have that dot and dot dot. So these two are the hard links that you can see here. And this single dot, the first line, this will keep information about current folder or current directory where we are in. And the dot dot will keep information about the folder above, so about its parent directory. That means if I run stat dot, I get the information about current folder, and I'm currently in home Marek. And if I run stat dot dot, so this one, I get the information about one folder above, about parent folder, which is /home. One sec, let me do it again. Stat dot dot means I should get the same information if I run stat home. And that's true. The inode 1728, the inode 1728. And that one has 4 links. So let's have a look. Remember to run lsla to see the hidden information as well. So you start getting the idea. The hard link is created for those 2 special entries and for any subfolders you might have inside current folder. We are now in home. Let me clear that again. So we are in home, yes? Stat for this folder is 1728. What's stat for folder above? And what is folder above, first of all? Folder above is a root folder, it's just /. And you will see interesting thing, because inode for root folder nearly always will be inode 2. Because inode ID of 0 and 1 are reserved, so inode ID with number 2 is the very first one that can be used when file system starts building that tree structure. and it always starts with root folder. That's why the root folder will always have the first available inode identifier, which is inode2. And all that information kept in directory inodes helps file system to build that entire tree-like structure, starting from this root directory and going down. And each directory inode will keep track of its own inode ID, about inode ID of the parent folder, and will also store information about file names that user might create or system might create inside its directory. And for each of those file names, it will keep the corresponding inode identifier. And we already saw that in previous examples. Okay, so that's all really what I wanted to say today. And I know this subject is not the easiest one. It's pretty difficult, it's a lot of moving parts, you know. But I hope that you find this video helpful. So thank you for watching. Marek.